without further delay, here's your instructor.
Hello, I'm Ron Bilyeu. I'd like to welcome you to our presentation, Focus on Fords. We're going to be going over some technological advancements in the Ford engine management systems. So let's get started. The first engine management system or input that I'd like to talk about in the Ford system is in model year 2011, Ford started utilizing a digital mass airflow sensor. Of course, Ford has had mass airflow sensors as far back as 1986 in the introduction of the California Model 50 Mustang and Mustang GT. All those years from 1986 up to 2011, the gas engines pretty much used an analog mass airflow sensor. If we used a voltmeter or a scan tool PID and we were looking at the output signal of the analog mass airflow sensor, we would probably see just under a volt on a hot engine base idle, and then we would max out at about 4.8 volts at wide open throttle on our analog mass airflow sensor. The diesel engine and the Power Stroke engine family, the 6.0, utilized an analog mass airflow sensor. The 6.4 used a unique mass airflow sensor, is what I call a combination mass airflow sensor. It not only provided airflow information to the computer, but it provided ambient air temperature in the air cleaner housing where the mass airflow combination intake air temp sensor was located. It had 6 wires, but it was a digital mass airflow sensor. One of the quick things when you open the hood and you're identifying, say, a newer Ford vehicle, if you see 4 wires going to the mass airflow sensor, you know that it's a digital mass airflow sensor. If you see 5 or 6, you know it's an analog mass airflow sensor. Taking a look at the transfer function, as it's called on a Ford, on how the computer looks at the input information, which will be a digital frequency in hertz, how does that convert into airflow, such as grams of air per second? This is known as the mass air transfer function. You see the mass air transfer function here at a low frequency level of approximately 1.5 kHz or 1500 hertz. That would be equal to approximately 1.83 grams of air per second. Now the mass airflow sensor can go all the way up to 12,000 hertz. In the mass air transfer function, which is in the programming of the computer, 12,000 hertz will equal 514 grams of air per second. So in the analog mass airflow sensor, we idled around just under a volt and we peaked, or we hit what was the max of the mass airflow sensor voltage at around 4.80 volts. On the digital mass airflow sensor, we're going to idle around 2,000 hertz, obviously depending upon the size of the engine, and we're going to max out at approximately 12,000 hertz, again depending on the size of the engine, or up to 514 grams of air per second. Along with this new digital mass airflow sensor, we have a new trouble code, P0068. It's the relationship on later Fords that not only have a mass airflow sensor, but they also have a manifold absolute pressure sensor. There is a sensor relationship parameter that's looked at by the computer. Let's face it, the computer knows the engine size. It knows how much air is flowing into the engine from the mass airflow sensor. There should be a certain amount of manifold pressure equal to the airflow coming into the engine. If these get too far apart in the parameters, it will set the code P0068, which the quick definition of this code is a rationality check. The amount of airflow doesn't match the manifold pressure, or the manifold pressure doesn't match the mass airflow, so the computer's keeping everything in check. As I said earlier, as we can see here on the slide, the 6.0 Power Stroke, if you look at the letter identification of the wiring, you see an A, B, C, D, E, F. So right away we know this is an analog 0 to 5 volt sweep mass airflow sensor. Right after the 6.0 Power Stroke, we went into the 6.4 power stroke. This is that combination mass airflow sensor intake air temperature. Now it is the first diesel Ford utilizing a digital mass airflow sensor, but because it's a combination mass airflow sensor, you'll see an additional 2 wires for a total of 6 for the thermistor and the intake air temperature sensor. And then in 2010, with the introduction of the all-Ford 6.7 Power Stroke engine, we have the digital mass airflow sensor that's very similar to what we see in the gas engines and pretty much the same frequency spec. Now, what is a mass airflow sensor used for on a diesel engine? Basically, when the computer asks for EGR flow, the feedback on how much EGR flow, exhaust gas recirculation, is entering the intake tract, it looks to the mass airflow sensor for feedback. It's required through OBD2 requirements that we know that exhaust gas recirculation is actually making it into the intake tract. Even though the EGR valve may have a position sensor, we still need to know, did the exhaust gases make it into the intake? So on a diesel, it's for EGR flow, but on a gas engine, it's probably the highest priority input sensor. It tells the computer exactly down to grams of air per second how much air is coming into the engine, so the computer will know how much fuel to deliver by controlling the injectors. We've got some checkpoint questions we want to go over here regarding the digital mass airflow sensors. So I'm going to take you to my first question, which is true or false. A Ford digital mass airflow sensor can be identified by having 4 wires. I'm going to give you 10 seconds or so to answer the question.
Hey Ron, it looks like our online audience is 100% true.
Absolutely, that's great. The only exception to the rule is we would have a digital mass airflow sensor on the 6.4 Power Stroke because it's a combination mass airflow intake air temperature. For the most part, if you see 4 wires going to the mass airflow sensor, you know you're going to have to check that with a meter that reads frequency or a lab scope or some way that you can check that frequency on a scan tool, because it is a digital mass airflow sensor. Let's move on to our next question. True or false, the frequency range of a digital Ford mass airflow sensor is 1.5 kilohertz to 12 hertz or 12,000 hertz. And I'll give you a few seconds to answer those questions.
All right, Ron, on this question, our online audience is saying it's false.
It's absolutely true. 1.5 hertz is the low side of the scale, which would indicate approximately 1.83 grams. Remember, this year Ford has a 3-cylinder 1-liter engine that might only flow 1 to 2 grams of air per second. The high side of the scale, 12,000 hertz, is 514 grams of air per second. We're going to move on here, and we're going to talk about a unique feature on the EcoBoost engine lineup. Now, Ford has really embraced this technology. Technology I'm speaking of is gasoline direct injection and turbocharging. Now, the control of the turbocharger is called closed loop boost control. So I want to discuss that with you. As you can see here, I have a shot of the EcoBoost turbocharger, and in the right-hand corner, you can see that we have an external wastegate actuator. Also, we want to talk about the technological advancements of the turbo itself. They're using some super alloy M246 tungsten carbide super alloy that really increases the strength of the turbine on the turbocharger. It makes it really lightweight and really strong so that we can reduce the turbo lag and the spool up time and get rid of any turbo lag we may have, and keeping in that the computer controls the boost pressure very closely with closed loop boost control. Let's take a look at that. Here I have a vacuum pressure schematic of the closed loop boost control system. So if we had manifold pressure directly attached to the wastegate canister, boost pressure would be controlled by the spring tension in the wastegate canister. Most systems will bleed off that pressure, which will change the gate and increase the velocity of exhaust flow to the turbine, thus increasing the turbine speed and the turbo boost pressure. So that bleed of pressure between manifold pressure and the wastegate canister is controlled by a wastegate control solenoid. It is a low side ground controlled duty cycle to that solenoid. Now the closed loop part is that some EcoBoost engines will be able to monitor the pressure in the wastegate canister. So if you have a Ford F-150 twin turbocharged 3.5 liter, obviously you have two turbochargers and you're going to have two wastegate canister pressure sensors. So as it's manipulating the pressure in the wastegate canister, it knows exactly what the pressure is. Also, we're going to have a bypass valve, or it could act as a blow-off valve that's 100% electronically controlled by the computer. So if we go in an overboost condition, it can quickly dump off the boost pressure. That bypass valve is also used when the computer detects decel. It can bleed off the pressure in front of the throttle plate, quickly bleeding off any pressure that may cause pressure waves in front of the throttle plate. So let's look at some of these components individually. Here's a shot of the wastegate control canister valve. The computer has a pressure sensor that watches that pressure in the wastegate canister on some EcoBoost applications. Now we can move on to the compressor bypass valve. There's no vacuum hose going to this. It's not controlled by vacuum or pressure as we typically see a bypass valve. It's electronically controlled by the computer. So the computer can open and close this valve, and it also knows the position of the valve for deceleration bypass and for overboost conditions. It can quickly go to that valve and open it. Here we have the actual wastegate solenoid that's low side controlled duty cycle that bleeds off the pressure between manifold pressure and the wastegate canister. The computer controls the ground side of this, thus controlling the desired duty cycle. Watching the feedback from the canister pressure and manifold pressure, it has very precise control and of the boost pressure. So we've got some checkpoint questions that we want to go over regarding EcoBoost closed loop boost control. We'll go to the first question. Closed loop boost control is utilized by the following inputs and outputs. A, wastegate solenoid. B, wastegate pressure sensor. C, wastegate control actuator valve, or D, all of the above. I'll give you approximately 10 seconds to answer the question.
All right, Ron, on this question, the majority of the audience, 80% of them says it's all of the above.
Absolutely correct. The wastegate solenoid, the wastegate pressure sensor, which we may have two on a twin EcoBoost engine, and the wastegate control actuator valve are all part of the EcoBoost closed loop boost control system. An additional item I'd like to point out on the EcoBoost system, remember this is a forced induction engine. We need vacuum to assist our power brake system. So you may see on some EcoBoost engines, for example, this is a cutaway of the Mustang 2.3 liter EcoBoost engine. It's a cutaway of a camshaft driven mechanical vacuum pump so that we can rest assured that we always have enough vacuum for the brake booster. Now Ford will either utilize this mechanical pump for additional vacuum for the brake booster, or it may use an electric pump that may be found behind the left front headlight, such in the cases of Ford F-150. So either one of these may be utilized to provide additional vacuum for brake booster operation. Also, on an EcoBoost engine, we have to realize that if we have a positive pressure in the intake manifold and the computer's commanding a purge of the evap system, there could be some danger as far as pressurizing the fuel tank, especially when we know that we may end up with a fuel mixture that's close to perfection or stoichiometric. That could be really dangerous. So Ford on the EcoBoost engine is using a special dual path purge for the turbo system. As you can see, if we happen to be purging during normal engine operation and we're not in a boost situation, we're going to flow from the charcoal canister, the fuel tank vapors, through the canister purge valve and move right into the intake manifold under vacuum. Now, if we're in a boost situation, the ejector valve, you can see, is tied to positive pressure and the suction side of the turbo. So we're going to route the fuel tank vapors in front of the turbo inlet and let it go that way instead of possibly pressurizing the fuel tank to protect any pressure in the tank. So this is a unique evap system that is utilized on the EcoBoost system because we're pressurizing the intake so we can still purge the evap vapors even in a boost situation. The slide that you're seeing here says no barrow to hidden barrow, and let me explain this. For many years, technicians might be looking at their scan tool and they will see a barometric pressure PID that's in hertz or frequency. Now, if they looked up the specs, they would find out that the specification is 158 to 160 hertz at sea level. For every 1,000 feet of elevation, the frequency drops a couple hertz. So let's say your shop is in Florida near the Gulf of Mexico. You're probably going to see, depending on the weather conditions and the atmospheric pressure, somewhere between 158 and 160 hertz. But today you're looking at the scan tool and you see 143 hertz. It's way out of spec. Well, I must have a defective barometric pressure sensor. There's not one. It is a calculated or inferred value that is really triggered off of the mass airflow calculation. The tip here is that it can be helpful to you. It's a dead giveaway that you have an undercalibrated or contaminated mass airflow sensor. The exception to this rule would be if the EGR valve is called an EGR system module that has the EGR control solenoid, DPFE sensor, and EGR valve all in one unit, or the total electronic stepper motor EGR valve, you'd have a separate map sensor that is the barrow. But if you have a normal EGR vacuum operated EGR valve with separate EGR control and DPFE sensor, then it's calculated or inferred the frequency. Now what about if you look at the frequency and it says it's 172? If I was helping a technician with a problem vehicle and he says, Ron, what's really weird is that my barrow frequency is 172 hertz. My very next question to him would be, does this vehicle have an aftermarket turbo or supercharger on it? If his answer is yes, then the tuner that tuned for the turbocharger or supercharger does not have the mass air transfer function correct. Now, if it does not have an aftermarket turbo or supercharger, then we're going to know that the mass airflow sensor is over-reporting airflow and load, and really the only fix for that is to replace the mass airflow sensor. Now moving to newer Fords with the EcoBoost engine family. We actually have a barrow, but it's kind of hidden. The barrow sensor is internal to the Bosch PCM. So now if you see frequency that's off or doesn't match your current atmospheric pressure, then you're going to possibly have to replace that Bosch PCM because the barrow frequency or the barometric pressure sensor is internal. What we have during key on engine off is a pressure sensor correlation check. Let's take, for example, that we have a Ford F-150 twin turbo that has two canister pressure sensors, plus it's got the turbo inlet pressure sensor mounted on the charge air cooler, and it has the manifold absolute pressure sensor, and it has a baro sensor in the computer. That's a total of 5 different pressure sensors. The tip is check all pressure sensors at the same time, key on, engine off. For the most part, I would say in my career, over 30 years, 90% of any failure of a pressure sensor, it will show up under key on, engine off. So do your pressure sensor correlation check, key on, engine off. So as you can see, key on, engine off, you may have turbo inlet pressure, manifold pressure, wastegate canister pressure, and the baro sensor. Here is the baro transfer function, how voltage and pressure are correlated to the computer from the internal barometric pressure sensor, known as the transfer function. There's our 5 pressure sensor check. Now obviously if you're a naturally aspirated late model Ford engine, you may only have baro pressure and manifold pressure. But most of the naturally aspirated Ford engines have mass airflow sensors. So we're typically talking about forced induction EcoBoost, which could have up to 5 different pressure sensors. There's our wastegate pressure sensor, which we may have up to 2, the transfer function for it. Now some of the manifold pressure sensors found on the intake manifold come in different varieties. We may have a 2-bar manifold absolute pressure sensor. That means it can read atmospheric pressure up to approximately 15 psi, then positive pressure of another atmospheric pressure or 15 psi. This means it could read up to 15 psi of positive boost pressure. Well, wait a minute. I've seen the Mustang EcoBoost in the right conditions spike up to 22 to 23 pounds of boost. In that case, we would exceed the limit of the 2-bar pressure sensor. So Ford does have, in some applications, a 3-bar or 3 atmospheric pressure sensor that could read up to 30 psi of positive boost pressure. And in some applications, this pressure sensor is a combo sensor, kind of like the digital mass air intake air temp sensor on the 6.4 Power Stroke, only now it's a mass airflow sensor, intake air temperature sensor all in one unit. But it can read up to 30 psi, and there's a shot of the transfer function, how the voltage is converted into pressure for the computer. Here we have a technician that's using his snap-on Virus and just showing that he's doing a simple correlation check between barometric pressure and manifold absolute pressure sensor. You want to look at your PID list and pick every pressure sensor that you have and do your correlation check under key on, engine off. Another tip I'd like to give you, if you have the luxury that vehicle that you're doing your pressure sensor correlation check has set overnight, this is an opportunity to do a temperature correlation relation check. You may have ambient air temperature, coolant temperature, cylinder head temperature. This is a good time to go in and make sure all of those are within a few degrees of each other. Now your correlation on pressure should be within 2 kilopascals or 1 psi of each other. Your temperature, probably a couple degrees Fahrenheit, depending on where these various temperature sensors are, mounted on the engine compartment. We're going to go into some checkpoint questions here. The first question, the following pressure sensors are checked for correlation during key on, engine off. A, baro sensor. B, manifold absolute pressure sensor. C, turbocharger inlet pressure sensor. Or D, all of the above. We'll give you some time to answer that.
Okay, Ron, it looks like our audience has picked 89% being all of the above.
Absolutely correct. Baro, manifold absolute pressure, turbo inlet pressure should all be checked during key on engine off. And if you have the additional wastegate pressure sensors, those should also be checked. We're going to move on to the next question. True or false? Up to 5 pressure sensors can be checked for correlation key on engine off. I'll give you some time to answer.
It looks like 86% of our audience is going with true.
Absolutely correct. It is true. If we have a twin turbo F-150, we'd have 2 wastegate pressure sensors, turbo inlet pressure, manifold pressure, and a baro sensor inside the computer for a total of 5 different pressure sensors that should be checked key on, engine off. Moving on to another important system in the Ford engine management system is electronic throttle control. We know that all manufacturers are embracing electronic throttle control. It yields many benefits to the manufacturer, such as torque management, no additional components for cruise control, better engine management. It's easy to come in and out of multiple displacement systems, such as displacement on demand or multiple displacement system. It really just helps all of the systems work together. Now, this Ford system does have some pretty complex hardware and software. Inside the PCM, the hardware that controls the electronic throttle control is known as the eQuizer processor module. Now, we're all familiar with check engine lights coming on, but may be alarmed if we see the little orange wrench light come on. If the orange wrench light comes on, it's an indicator that you have a problem in the electronic throttle control system. Now, the hardware, known as the eQuizer processor module, then we have the software known as the integrated plausibility check software. So it's kind of a system of checks and balances. The computer is using the software and using what's called algorithms. What if this happens? What if the computer sees a failure? How does it react? And there's a name for this. It's called failure mode effects management. So if the computer sees a fault, how is it going to react? Every manufacturer has to be concerned about the fact that we don't have a physical cable going from the pedal to the throttle. It's totally electronic controlled. No one wants unintended acceleration. So we look at some of the strategies of the failure mode effects management. Depending upon the software and how severe the fault is. The first level may be just limiting RPM not to go over, say, 1,500 to 2,000 RPM. The problem's a little more severe. It may not let the throttle open and limit RPM, so you're pretty much stuck idling. However, if you think about it, if you were in the Midwest and it was 10 below zero and the computer detected a problem, at least the engine would still idle. So if the engine's still idling, the engine is still operating, you still have heat. Pretty much the third stage of a problem is it may only idle and it may disable things such as intake manifold runner control, variable cam timing, or some of the other engine management and emission controls that it may be operating. If the problem is severe enough, before the computer does a total engine shutdown, meaning the engine won't even run, it's going to enact some PCM resets. It will do several of these and count up to a certain amount, whatever the engineer programmed in, but it'll tie a PCM reset to see if it can solve the problem. Kind of like when your computer at home is doing something weird and you reboot it. So the computer keeps trying to reboot the system to see if it can improve the problem. Eventually, after it runs out of reboots or resets, it's going to do a shutdown and not even let you start the vehicle. But there's several strategies known as failure mode effects management in the electronic throttle control system. The hardware controls the H driver. The H driver controls power and ground, high and low side control to open and close the throttle. The computer really watches the current flow of the motor to open and close the throttle. So if you get carbon buildup on the throttle plate and it resists the opening, the computer may detect that and start to go into some backup strategies, and along with that, possibly set up some trouble codes. Now, after you've either cleaned or you've replaced the throttle body, you need to look into your scan tool and see if you have any type of idle relearn procedures and system tests in your scan tool. If you don't find any reset procedures in your scan tool or idle relearn procedures, I always kind of go through letting the engine run in park, a hot engine, let it run in drive, a hot engine, let it run for a while hot with the engine idling, with the air conditioning on. Pretty much as you see here, let the computer, give it time to do an idle relearn strategy. So if you don't have that process in your scan tool, make sure that you give the computer time to do the relearn. And it may take up to 15 minutes. We've got a checkpoint question at this point we want to go over. True or false? The internal software that operates failure mode effects management for the electronic throttle control is known as the eQuizer module.
Ron, it looks like our audience is going for 75% true.
It's actually false. The eQuizer module is the hardware. The software is known as we back up here, the software is known as the Integrated Plausibility Check software. The hardware is known as the eQuizer module. Not so important that you know the names of them, but definitely you need to know how the computer reacts to these problems so you'll know how to check or properly diagnose the vehicle. The next area we're going to go into is I have a case study that I'd like to share with you. We have a 2009 Ford Flex that the customer complaint was a misfire and a check engine light. So what we're going to do is we're going to use some new diagnostic scan tool known as the Molly scan tool. We're going to use this tool to help us diagnose and repair this 2009 Ford Flex. So let's go to the shop and get to work on this Ford Flex. In the shop here today we have this 2009 Ford Flex. It's got a check engine light and the customer's complaining of a chuggle and a misfire. So we're going to run some diagnostics on this 2009 Ford Flex. Every technician across the country will probably, one of the first steps they'll do is to utilize the scan tool, and they'll go in and check for codes. As a technician, you want to separate yourself from other technicians as far as your diagnostics. I highly recommend that you do what I call an all-system scan. Sometimes you'll see a Toyota, Lexus, Scion, they'll call it a health check. Don't just be like a garden variety parts house and walk out with a global scan tool and check just codes, or I should say global or generic codes in the PCM. Check for codes in every module. Modules like to tell on each other. Not only that, it generates additional revenue for the shop in work in other areas such as brakes, heating, ventilation, air conditioning, steering, door modules. It goes on and on. Most vehicles have a minimum of 6 modules on the vehicle. With the Mala scan tool, there's no excuse. You will not believe how fast I can check all the modules on this 2009 Ford Flex. So the first thing we're going to do is the all system scan. So I click on diagnose. It's connecting Bluetooth to the vehicle communication interface. So we're going to go into the all system scan, what Molly calls the vehicle-wide diagnostics. So you can see how quick it is. It's running through, checking all the modules on this 2009 Ford Flex. And very quickly, it's checked all 12 modules. As you can see, the only module that has trouble codes is we have a P1000, which means that the monitors have not been completed. We have a P0355, ignition coil primary. So now we're going into some special tests with our MALA scan tool. Let's first take a look at cylinder balance. We know we have a customer complaint of misfires, and we have a P0355 for ignition coil primary problem. Let's go ahead and start the engine. We can definitely see that cylinder number 5 is a lower cylinder in the cylinder balance test than the other cylinders. So let's go in, let's shut the engine off. Even though we know we have a diagnostic trouble code for cylinder P0355, primary ignition failure, and we know we have a miss in our special cylinder balance test, let's make sure we don't have any mechanical problems. The MALA allows us to do a special relative compression test. So we'll get set up for that. When you're doing the relative compression test, as it says on the MALA tool, you want to apply the accelerator to full throttle and then crank the engine. At full throttle and cranking RPM, the computer will turn off the injectors in what's known as a clear flood mode. So let's go ahead and crank the engine. Okay, so we know we have good compression. The mechanical condition of our Ford Flex is in good condition. We have a code P0355 for ignition coil. So I broke out the lab scope, the snap-on Virus, and I'm going to current ramp the coil on cylinder number 5 where the misfire was occurring. Remember, we detected the misfire on the cylinder balance test in our MALA scan tool. So now we're going to use the lab scope and do some pinpoint testing of number 5 ignition coil primary. As you can see here, if we look at the ramp, the bottom here trace on our Virus, we have a vertical line going up. That's a dead giveaway of a defective shorted coil. Two things we're seeing here. We've got the vertical line in the current ramp, which is a dead giveaway, and we have low firing voltage on our primary side of that coil. Definitely two things that are dead giveaway that we have a defective coil. We're able to look at the primary voltage pattern on this coil because this coil only has 2 wires. It's not a smart coil. The switching transistor is in the PCM, which gives us the ability to connect to the negative or the primary side of the coil to look at voltage and amperage. So we definitely have a defective coil. Let's replace that coil or move it to another cylinder, see if it moves, and see what a good coil looks like. So let's connect to a good coil and see what a good voltage pattern and current ramp pattern looks like. Okay, now we've connected to a known good coil. You can see the top trace, we have a good inductive kick. We see the transistor turn on, the dwell section, we have a good inductive kick, and look at our current ramp pattern, a nice smooth upward ramp indicating that we do not have any shorts in the coil. So the misfire, the trouble code was all caused from a defective number 5 ignition coil. So we have a successful repair of the 2009 Ford Flex. We replaced the coil. Customer's happy, really great repair. I want to say my first experience with the MALA scan tool was very impressive. It's amazing how fast it can run through and check the codes in all the modules and how all the tests were operated. I'm really impressed with that tool, and I'm sure technicians will enjoy using it in further diagnosis. The next case study that I'd like to go over with you is a 2015 Mustang. It runs rough, it hesitates, it has some misfires, mainly when the engine's code. Initial checks, we do not have any trouble codes. The fuel trims look in spec. So this time we're going to use the Ford factory tool, the IDS, and do our diagnostics with it. Let's go to the shop and get to work on this Ford Mustang. We have a case study on a 2015 Mustang EcoBoost engine 2.3 liter. The customer's complaint is runs rough, hesitation. It mainly runs rough and has a hesitation, seems to be worse when it's cold, and it skips, as the customer said, and has misfires. We did not, when we run our diagnosis, we did not have any diagnostic trouble codes, and the fuel trims look within spec. Our short term was dancing between -5 and +5%. Our long term was in check within -10 to +10%. So because we had some misfires, where would you go to next if you don't have any current misfire data? And probably Murphy's Law, you're working on it right now and the engine's warm and the customer's complaints when it's cold. Well, we wanted to shed some other light to see if we could find any type of misfires hidden inside the Ford processor. Where you want to go is mode 6. And in mode 6, it is required by the federal government and the CAN network to show you misfires in mode 6. So we used our Snap-on Virus and went into mode 6, and we start to look at here, take a look at what we found in mode 6, looking at individual cylinder misfires. As you can see here, mode 6 misfire number 1, we have a pass, but we had a single cylinder misfire, just a number 1 there. Moving on to cylinder number 2, the value was 0. Absolutely no misfires were detected on cylinder number 2. On cylinder number 3, again, we had 0 misfires. So we moved on with the Virus, and we did come to cylinder number 4 that had the highest amount of misfires, which was a 5. So we believe the customer. There are misfires occurring, and through some research, it seems to be a common problem with the EcoBoost engines, cold engine misfire, typically after they've had about 20,000 miles on them. Even though we don't have any diagnostic trouble codes and our fuel trims look okay, I want to cover some system tests that are available to us in the IDS. Make sure we cover all of our bases. The first test I'm going to go to is a misfire test on the IDS. We're going to turn the key on, start the engine, and now it's going to run a misfire monitor. We pretty much want all the individual cylinders, 1, 3, 4, and 2, to stay above the red line. We do have cylinder 4 that got close. Remember, cylinder 4 was also the cylinder that had some misfire counts on mode 6. We're going to move from the misfire monitor test back into powertrain, take a look at power balance test. Now we can see our power balance test. It's actually monitoring the torque output per cylinder, 1, 3, 4, and 2. You can see as there's any loss of RPM after cylinder firing event, it drops down into a V shape. When they do drop down, you see they're dead center. Let's say we had particular cylinders that were misfiring, were dropping down, but the V is shifted to the left or the right. The tip I'd like to give you for that, it means that the misfire is caused by valve timing and not an ignition or fuel misfire. So there's some variation going on here, but nothing really standing out. You can see we're allowed pretty much plus or minus 25 RPM in the scaling. Cylinder 2 did have a little more of a misfire than the others, but nothing really standing out as a dead misfire. Go back to our testing sequence. Misfires look okay. We're going to run some fuel tests, some fuel system tests. So we're going to go ahead and turn the engine off. And we're going to first run our low pressure test. We want to turn the key on. Make sure we're out of the power balance test. Fuel pressure test. Key on, engine off. In our GDI system, we have a low pressure and a high pressure. It's running through doing a systematic fuel pressure and leak down check. Fuel pump pressure on was 108.8. Off pressure, residual, making sure that we don't have any leaking injectors, a leak at the pump assembly, looks good. Then they have a 10-second gross leak pressure, should be above 68 psi. It passed that test. Now it's doing the final leak down test, which is a 60-second leak down pressure test. So far it's looking good. Whenever you're checking a gasoline direct injection system, you want to start with the low side and do a low pressure test and then move on to the high side. It's nice to have the Ford factory tool, the IDS, that automatically does a systematic low pressure and high pressure injector flow test. So we're just now coming up completing the low pressure test, and we've passed fuel pump on pressure 108.8, fuel pump off pressure 97.7, 10-second major gross leak pressure 96.7 psi, and a 60-second leak down so we don't have any leaky injectors, fuel pump check valve, any problems there, all looks good. So let's move on to the high pressure test. We'll move on to the high pressure test, telling us how to set up for the high pressure test. Turn the ignition key off. Now switch the key on. We want to make sure the battery has sufficient charge. We're in park. The engine will be cranking in 3 seconds. As you can see here, the injector flow test, or what we call a relative injector flow test, the high pressure system, each individual cylinder come out at 140 milliseconds, showing us that we have really good injector flow. We don't have any misfires that are really showing up other that are stored in mode 6. Our fuel delivery low side, high side pressure test pass. Injector flow test pass. From looking at the intake manifold, it looks like from oil residue that we want to inspect with our bore scope and see if we have any carbon buildup on the valves and how we're going to address it. We did an inspection at the throttle body and we noticed there was a lot of oil residue. So we decided to dig a little deeper and break out the bore scope and start looking for carbon buildup in the intake manifold runners and behind the intake valves. As you can see here, we can definitely see the results of the carbon buildup on the back of the intake valves. Now this seems to be a big controversy in our industry on how would you repair this. If the vehicle is under warranty, and this is a little hard to swallow, but at the Ford dealer, they might choose to replace the entire cylinder head. Obviously, the rumor mill is that in some testing of using chemicals to clean the carbon off the valves, which technicians we've done for years, there was some carbon that got dislodged from the combustion chamber or behind the valve and made its way in and damaged the turbocharger. So they feel that by chemically cleaning, there is a risk, one, from carbon being broken off and damaging the turbo, two, that during the cleaning process there are elevated temperatures. But I want to remind you what we looked at earlier, that the alloy of the turbine is over Rockwell 60 tested. It's a super alloy that's being used. So we're at a point here, do we want to make a choice? Do we want to risk possibly damaging the turbocharger, or what are some options that may be out there? So let's look at what our options are that is going on in the industry. One is a chemically cleaning. We have to concern ourselves that we're not going to do any damage to the turbocharger. In the early 80s, there was a machine developed called a crushed walnut shell machine, in which you would remove the intake, possibly rocker arms or cam, close the valves, and shoot crushed walnut shells that would kind of bead blast the back of the valves, and then you would vacuum them out. If there was any little pieces of walnut shells left, they would just burn up in the combustion process and not have any detrimental damage to the engine. There's not very many shops that still have these crushed walnut machines laying around, so that option is pretty tough. Cylinder head replacement, that's rather expensive. Now, I would like to add something here that only one manufacturer has decided to fix this problem with. This year, BMW does have an M engine that has water injection. You can imagine whenever the engine is under a certain amount of load, if we would interject some water or water methanol injection, it would keep everything super clean. As a technician, I'm sure we've pulled the head on an engine with a blown head gasket, and we know exactly what cylinder the coolant has been going into, because that cylinder, spark plug, valves will be whistle clean. I believe that water methanol injection is probably the future of some of these direct injected turbocharged engines that every manufacturer is utilizing. Only BMW at this time has chosen to use water injection as a viable way of keeping the back of the valves in the combustion chamber clean. You see, we don't have an injector shooting fuel to the back of the intake valve. In direct injection, it's shooting it directly into the chamber. The other option that is used by the BRZ engine, some Lexuses, known as the D4S system, is it has gasoline direct injection and port fuel injection. So you still have a port fuel injector that's spraying fuel directly to the back of the intake valve, keeping it clean. Some technicians are using water injection in the field. They've made their own apparatus. They go out and drive the vehicle rather aggressively, letting water injection in to help dissolve and clean the carbon, and some of those guys are getting some good results from those. We've elected, after talking with the customer and explaining to them the features and benefits of the CRC, we're going to go ahead and do the CRC cleaning on this 2015 Mustang. One of the cleaning systems that I've used in the past and have some experience with, and maybe some technicians out there also, is a motor vac cleaning machine. What was the gauge on the motor vac cleaning machine? You guys that have used one know that it was a vacuum gauge. What did Snap-on want you to do? They want you to look at the vacuum before the cleaning and after the cleaning. Well, this 2015 EcoBoost engine has its own built-in boost pressure, vacuum, and even air-fuel ratio gauge built right into the instrument cluster. So we're going to take a look after the cleaning at engine vacuum, what it was at idle before and after, just like we used to do with the older motor vac type snap-on cleaning machine. Then we're going to keep the vehicle overnight and make sure that we've got rid of the customer complaint, the hesitation, and cold engine misfires. The directions on the CRC IVD cleaner tell you to administer the cleaning spray behind the mass airflow sensor. Obviously, we don't want the cleaner hitting the hot wires or the hot film in a mass airflow sensor. But wait a minute, this 2015 Mustang is EcoBoost. It does not have a mass airflow sensor. So what we're going to do is directly shoot the cleaner into the throttle body itself, because we can remove the snorkel from the throttle body and the engine will run normal, and we can introduce the cleaner, making its way past the throttle body, through the intake valves, combustion process, cleaning the combustion chamber, the back of the valves, the spark plugs, the oxygen sensor, and even possibly cleaning the monolithic brick of the catalytic converter, and do a good cleanup job of all of this. Okay, we have completed the CRC IVD cleaning process on the Mustang EcoBoost. Now, I told you I was going to do a test. Let's look at those results. I've got a shot of engine vacuum and RPM before the cleaning. As you can see here, the boost vacuum gauge in the center of the dash is about 18 inches of vacuum, and the RPM is idling somewhere just under 1,000 RPM. So pay particularly close attention that the engine vacuum is 18 inches and just under 1,000 RPM. This is before the cleaning. Now, after the cleaning, pretty much the same engine temperature. Notice the tachometer is in the same exact position, hot engine base idle, below 1,000 RPM, but look at our engine vacuum now. We're just a hair over 20 inches of vacuum. So we picked up a solid 2 inches of vacuum after the upper induction cleaning. So there you can see the 18 inches, and after the cleaning, just a hair over 20 inches of vacuum, showing you that you have improved the induction system and the flow of air to the engine by doing a cleaning of the upper intake, the combustion chamber, spark plugs, oxygen sensor, the back of the valves, and possibly even the catalytic converter. We're going to let the vehicle set, make sure that we've taken care of the customer problems, cold engine, but we can already tell that the engine is idling smoother and the throttle response is a lot more crisp. So our second case study, the Mustang EcoBoost, was a success. We've improved the idle, throttle response, no more misfires when the engine's cold. So the CRC IVD cleaner was a success. We have no apparent any damage to the turbocharger, and the engine's running really well.
Unfortunately, we're out of time. Thank you for attending our live stream, and we hope to see you again in future broadcasts.